Hi, welcome to my video on extra problem number 4 on the cooling effect. The cooling effect of water is an exponential function. A cup of water cools fast at the beginning and slows down as time goes by. It represents a decay curve. T represents, the large T represents the temperature of the water, small t represents time. So this is the temperature and this is the time. So the vertical axis is the temperature of the water and the horizontal axis is time. Notice I don't have a part of the axis. Notice I didn't go over here because the time starts at 0, and I didn't go down here with the extend the y-axis down to a negative because the temperature normally doesn't go below 0. Unless you have it in cold weather, but if the water's in cold weather, then it will freeze, so it won't go below. Just the water stays at 0-degree temperature. Let's do an example. And it's because this is a decay curve, representing a decay curve, it'll start here when t is 0, then it starts here and it goes down and it tapers like this. And there it is, decay curve. A 90 degrees Celsius cup of water is in a room whose constant temperature is 20 Celsius. The water cools to the room temperature. The 20 Celsius room temperature is the asymptote because the water cannot go below, normally would not go below 20. The water cools from 90 to 20, which is a difference of 70. So in this equation, that represents the exponential. T is the temperature, large T. A is the difference. B is the base, that is the power is raised to. T is the time. C is the increment change of time. And this is the asymptote. So K in this case is 20 because it's the room temperature. The water will go down to 20 degrees and won't go below it. And the difference between 90 and 20 is 70. So the equation, the temperature is 70 B T over C plus 20. That's in this problem. So what if we continue and say that the water cools at a rate of 20% every 2 minutes? Well, every 2 minutes C is 4. That's the increment change every 4 minutes. The rate is 20%. So the base is 1 minus the rate, which is 28%. So it's 1 minus 0.28. So the base is 0.72. So the equation now is T equals 70. The base is 0.72 T, and the increment change is 4, and the room temperature is 20. So that's the equation. Okay, let's turn to the next page. And let's look at that equation that I just wrote, which is T equals 70 degrees, and the base is 0.72 raised to the T over 4 plus 20. Notice it's T over 4. So that means if I want nice or good simple powers of the 0.72, then I like to be T to be a 0, a 4, multiples of 4. That'll give me integers, positive integers as a good power, single digit. So if I take the equation, so what I did, I drew a graph, and this is the temperature, is the vertical, this is time, and I did increments of multiples of 4. I just wrote some of them here, but I did extend them here. And notice that I have the, if I put 0 in the equation, take 0 for time, put 0 in, 0 over 4 is 0. 0.72 to the 0 power is 1. 70 times 1 is 70 plus 20. So when the time is 0, the temperature is 90. And we put 4 in, and we get a 1. So 4 divided by 4 is 1. So use a calculator and we'll get 4 brings us approximately to a 70 degrees. So we put 8 in. 8 divided by 4 is 2. So put this in your calculator and it comes approximately 56. Put 12 in, you get a 3, and you'll get approximately 46 to the nearest degree. Put a 16 in and you'll get a 4, and that gives you approximately 38 degrees. And if you put a 20 in, you get a 5, you get a, that's a 39 there. And put a 20 in, you get a 34, and you put a 24 in, you get a 30, and if I go down to 40, you'll get a 23. I didn't want to keep putting them in. So let's plot that, and you'll see that at 0 we have a 90, which is right there. At 4 we have a 70, which is right here. At 8 we have a 56, so 56 is roughly just almost in the middle there. At 9 at 12 I have a 46, 12 I have a 46, so a little bit more in the middle. And at 16 I have a 39, or almost a 40, so we just go close there. And at 20 I have a 34, 20 is a 34. You can see it's beginning to, it comes down fast and is slowing down now. And at 24 we have a 30. And at 40 gives me a 23, so 40 is a 23, so let's say it's approximately there. But because the room temperature is 20, we could say 20 would be the asymptote. In other words, the coffee will not cool anymore. But if we think about it and we draw this curve that's doing this, mathematically, this, it comes down. Mathematically, it goes on and on forever. But in the real world, that coffee or water would cool to the 20 degree late in the room. So that's just an example of graphing the equation to show you that it cools down fast and then it slows down as time goes by. And really, there's no asymptote here because the water will be 20 degrees in the room with a room temperature of 20. Let's look at another equation. T equals 80 times 0.7 raised to the T over 5 plus 10. And T is in Celsius temperature, and the big T is in temperature in Celsius, small t is in time, in minutes. The equation represents a cup of coffee in the outdoors. How much does the coffee cool? Well, the coffee cools 80 degrees. What is the outdoor temperature? 10. What is the maximum temperature? When you put a 0 here for time, you get 0. 0.7 to the 0 is 1. 80 plus 10. The maximum temperature of the coffee before it starts cooling is 90. What is the cooling rate? Well, the base is 1 minus the rate, and the base is 0.07. 0.7, 1 minus r. Move the r to the left, move the 0.7 to the right, and we get 0.3, so the rate is 30%. That's how fast it's cooling. It's cooling at 30% every 5 minutes. So that's 5 minutes. And the asymptote is T equals 20. The coffee will not go any lower than 20. And to do an example of that, the maximum temperature is 90 when we have a 0, and it's cooling down, down, down. Remember, it goes fast and then slows down, but the asymptote is 10, so it's 10. I'll draw the asymptote here. It can't go any lower than 10. So it starts to cool down and comes over and over and over. And as time goes by, it will get closer and closer. And again, mathematically, it won't touch, but in the real world, it will touch. It will be, the coffee will be a temperature of 10. Okay, let's continue. Let's reverse it. Let's write the equation and find the temperature of the water at 30 minutes. Let's see, a cup of 200 degree Fahrenheit water is placed in a 25 Fahrenheit room. 25 degree Fahrenheit. The water cools at a rate of 40% every 10 minutes. Find to the nearest degree the water temperature after. That's water. So a little misprint there. A little printer on the calculator. The water temperature after 30 minutes. So we have the maximum. So we have the maximum temperature to be 200. We have the K, which is the asymptote, to be 25. So that means the maximum temperature is A plus K. So 200 A plus 25. So A is 200 minus 25. So A is 175 degrees. And the rate is 40%. So the rate is, the base is 1 minus your rate, which is 40%. So it's 1 minus 0.4, which is 0.6. And C is 10. So when we have all that, the equation is T equals A, B, T over C plus K. And again, the large T is temperature and the small t is time. So we want to find out, after all that, we want to find what the temperature is at when the time is 30 minutes. So let's sub that in. What's the temperature? A is 175. B is 0.6. 30 over the increment change of 5 plus K is, the room temperature is 25. So we worked that in our calculator and we would make 30 over 5 divided by 5 is 6. So we can use our calculator and turn on the calculator, and we have, move that up a bit, we have 175 bracket 0.6 and exponent, and 6 is there, so we plug the 6 in plus the 25, and we get 175 to the 6 power. Okay, we get 33.16. So that's 33.16, and so the temperature to the nearest degree is 33. 33. And that brings us to the end of reviewing the cooling effect as a decay curve. And hopefully, if you enjoy my video, click on the like button, the subscribe button, visit my math website, www.mathfullyexplained.com, to find more information about me, my videos, the content that's on my YouTube channel called Math Fully Explained. Thank you for viewing my video. Hope the video helped you. Bye-bye.